take a look at an example of how to find the sum of a finite arithmetic series. Here we have our arithmetic series, 1 plus 4 plus 7 plus 10 plus 13. That is a finite arithmetic series. That is an arithmetic series because its terms would form an arithmetic sequence. 1, 4, 7, 10, 13 have a common difference of 3, with that making that an arithmetic sequence, so therefore this is an arithmetic series with that. And it is finite because it stops. It only has 1, 2, 3, 4, 5 terms in it. So if we want to go ahead and find the sum of this finite arithmetic series, you might be looking at me like, what in the world are you doing an example for this? I can add. Yeah, I know, I can too. I can look at this and see 13 plus 10 is 23, and 7 makes 30, and 4 and 1 makes 35. So the sum of this is equal to 35. I know that already. So why in the world would I give you a formula for doing that when I can just add up all the numbers? Well, I think I'm going to show you that here as I transition into a separate example where you can't see all of the numbers and you probably wouldn't want to go ahead and write them all out. But let's just go ahead and verify and show you how this formula works. So S sub n right here stands for the sum of the first n terms of the series, where n is the number of terms divided by 2 right there, and then multiplied by the quantity a sub 1 plus a sub n. A sub 1 representing the first term, a sub 1, I'm sorry, I don't know what I said. I don't know if I said a sub 1 or a sub n. But a sub 1 representing the first term of the series, and a sub n representing the nth term of the series that I'm trying to find the sum of. So if I wanted to go ahead and find the sum of this, I know looking at this there are 5 terms, so I have 5 over 2 times a sub 1 plus a sub n. A sub 1 is 1 plus a sub n, which is 13. So I go ahead and I add that up. I have 5 halves times 14. With that, 5 times 14 is 70. 70 divided by 2 is 35. So using that formula, I find the sum of the series to be 35. When I can see all the terms, I'm sure you can just add them all together and see that that's 35. You didn't need the formula, but hopefully as I transition into this next example, you'll see where that formula might be a little bit more useful, and we've verified that it actually does hold true by doing an example where we can just actually see the terms and add them up. So here we have a finite arithmetic series, but we don't actually have all of the terms listed. So it's not going to be as simple as that last one where you could just look at it, add up all the numbers, and have the sum of that finite series. You certainly could go ahead and continue and fill in all the other terms of the series and then add them up if you wanted to. That would take a long time, especially if I made this number something even larger than 99. So there's got to be an easier way. If you'd rather write them all out, have at it, but if you want to race, I'll do it the other way, and I'll win, I guarantee it. So what we really need to know to use our formula for the sum, I'm going to go ahead and put that formula back up there. We have S sub n is equal to n over 2, and then we had a sub 1 plus a sub n. So to find the sum, we need to know the first term, which we do, it's 4. We need to know the nth term, which we do, it's 99. But we need to know the value of n. That stands for the number of terms. And since I can't see all of the terms here, I might not know what that number of terms is. So let me show you a way that I can go ahead and find that number of terms for this. And it's going to come down to just writing the explicit formula for an nth term like we did when we talked about the arithmetic sequences. So we had that a sub n is equal to a plus n minus 1 times d, which was the common difference, if you remember that from when we talked about the arithmetic sequences. So let's write that explicit formula. We have a sub n equals the first term plus n minus 1 times d, the common difference, which I can look at this and I can see the common difference from term to term here is 5. Going ahead and distributing that to clean this up a bit, I have 4 plus 5n minus 5, and finally a sub n is equal to 5n minus 1 when I combine my like terms. So there's my explicit formula for the nth term of that arithmetic sequence, which is representing this arithmetic series here. So I'll go ahead and write that back up here. A sub n equals 5n minus 1. Now, if we want to know what term number this is in this series, all we need to do is plug that in for a sub n. So we have 99 is equal to 5n minus 1. And n stands for the number of terms. So I can actually solve this for n now and then know the number of terms. Adding 1 to both sides, I'll get 100 is equal to 5n. And dividing by 5, I'll get 20 is equal to n. So this series actually has 20 terms that I need to go ahead and sum for that. So now I have all the information I need to use my formula. I have my first term of 4, I have my last term of 99, and I know how many terms there are. That's 20. So I can go ahead and go back to my formula, which said the sum was equal to n over 2 times a sub 1 plus a sub n. N was 20, so 20 over 2 times a sub 1, which is 4, plus 99. So I have 10. 20 over 2 is 10. 4 plus 99 is 103. And 10 times 103, that's easy. Multiplying by 10, just add the 0 at the end. So I should have 1,030 for the sum of this finite arithmetic series.